Good evening, class. I ended up watching part 1 while I was doing some editing, and I heard that 1, my keyboard was a little bit loud, 2, there might have been a little bit of an echo, so I'm going to be changing a few things on this one, and hopefully it's going to be a little bit better. So, let's get into part B. This is the high-level concepts, this is the physiology behind the respiratory system. So, the first thing we really need to think about is, what function does the respiratory system serve? And yes, obviously, the main one you think of is breathing, but really hammer home why we breathe. So, first one, since we just talked about it, is breathing. The correct term for it is respiration. It's the process of bringing air in and bringing air out. Now, that is divided up further into 4 separate sections. We have pulmonary ventilation. This is moving air in and out of the lungs. Remember, when you see the word pulmonary, think lung. Following that, we have pulmonary gas exchange. So, pulmonary, in the lungs, gas exchange. We're exchanging gases. What would we be exchanging gases with at the lung? Go back to the pulmonary artery, go back to the alveolar, go back to the gas exchange, go back to why we're breathing. We are getting oxygen in and getting carbon dioxide out. So, pulmonary gas exchange is the movement of gases between lungs and blood. I have underlined this because there is going to be a different type of gas exchange soon. However, next we need to talk about gas transport. This is the movement of gases through the blood. Later on, we're going to be talking about how we get oxygen into the blood, how we get carbon dioxide into the lungs, as well as once we get to where that blood and where that oxygen is going to be going, the tissues, gas exchange at the tissues. So movement of gases between blood and tissues. It's going to be very important to know how, when you breathe in, remember, we're going through that upper respiratory system, lower respiratory system, passing through the conducting respiratory system into the actual respiration part of the respiratory system. Now, that oxygen that we just breathed in needs to get to the alveolar sacs, needs to have pulmonary gas exchange, so go from the lungs into the blood. The blood then needs to take that gas to the tissues where gas is exchanged there. Following? Perfect. Let's talk about the secondary functions of the respiratory system. I'm going to do them in bulk and then explain them. Now, remember, secondary things are not as important as primary ones, but still important to know, still cool to know, and then I'll let you know which ones will probably be on the test. We have mechanisms for speech and sound. The reason you are able to actually hear me is because of air. We have vocal folds, vocal cords, and when air moves through those, that's how we actually are generating sound. So the respiratory system is a critical part of actually be able to make sounds with our mouth. Granted, I can always just make sounds like this, but to actually have the advanced level of sound, you need a respiratory system. Also, 6:30 here, I got a lot of work left to do, so I made myself a cup of coffee. And I know you can't, but it smells amazing. The second thing is smell. We have neurons for olfaction in the nose. Now remember, our nose isn't smelling things, our tongue isn't tasting things, our eyes aren't seeing things. They are sending that information to the brain, which this is the organ that smells, tastes, and understands it. It's crazy. Next one, it aids in waste expulsion, and I'm breaking this into larger categories. So by increasing your pressure in your thoracic cavity, you are able to assist in waste expulsion. I would say at the risk of sounding gross, but I know that most of you here are in nursing or some form of healthcare. You are going to have to deal with gross things. We have all had that moment on the toilet where things got real serious and we had to take our shirt off. When you squeeze to assist in removal of waste, by increasing the pressure in the thoracic cavity, that can assist of getting things out. Another one I mentioned in class, but I think it's really cool, is you breathe out toxins. So, for example, alcohol is the easiest one to think of. It's broken down in your body at your liver, and then it is shunted through the blood. You can pee it out, you can poop it out, you can sweat it out, but another one is you can breathe it out. And this is how breathalyzers work. Now, of course, when you drink, they can register alcohol on your mouth and everything, but let's say that you've had a couple of drinks and then left the bar, but your mouth still smells like alcohol. It's not because there's still alcohol left in your mouth. It's because your body is breathing out alcohol to remove it as a waste product. Next one. Critical in maintaining the acid-base balance in the extracellular fluid. Now, acid-base balance. It's going to be important when we're talking about gas exchange and a few other things, but something cool to know. Next one, and this one is important to understand for the test questions. So out of all the secondary ones, this is the one that I would say, hey, pay attention to. It synthesizes an enzyme of angostin 1, which is critical for the maintenance of blood pressure and fluid homeostasis. So remember angostin 1, blood pressure, homeostasis. We're going to talk about it a little bit later. Now, though that is the basic overview of the respiratory system, broken up into its primary functions and its secondary functions. Now, let's talk about the methodology and the method behind the madness. I have here what purpose does the nose and nasal cavity do for incoming air? We talked about that in section A. We're getting into gas exchange now. So what happens at the alveoli and the respiratory membrane? Remember, what kind of gas exchange are we going to be doing here? Pulmonary gas exchange, because right now we're at the lungs and we need to exchange oxygen from the lungs, carbon dioxide in the blood, and swap them. So let's talk about this. Now, remember, the alveoli is really the location that respiration really happens. You have respiratory bronchioles, but imagine alveolar sacs as those little grapes, and the respiratory bronchiole as that grape stem. The grapes are where, that's the thing you eat. That's where most of the stuff happens. And they are, let's talk about what happens there. In the alveoli, there is the respiratory membrane. It is a fusion of simple squamous cells with endothelial cells. Now, simple squamous endothelial cells are classified at the lungs as type 1 alveolar cells. It's about 90%. Let's get a good look at a photo. Right here. As you can see, this respiratory membrane is that fusion of that simple squamous type 1 alveolar cells and the capillary endothelial wall. Now remember, back from the circulatory system exam, the capillaries only are one cell line thick. and the alveolar wall is only 1 cell line thick. This is a fused membrane to allow gases to be exchanged here. In addition, I did this in class where I balled up a piece of paper, but for the people who weren't there, let's talk about why the grape structure. How come they're grapes? Obviously they're not grapes, but they look like it. They're tiny small balls. That's to increase their surface area. Let me give you an example. This is also probably going to be super loud, so maybe I won't. I'll do it with this. Sticky note. There is still the same amount of sticky note. It's just taking up less space in the world. That's surface area. That's why they're small, tiny balls. If you would actually take all of your alveoli sacs and then spread out your lungs, it would cover half of a tennis court. It's massive, the amount of it. Also, the figure that I showed you earlier is figure 12.1. Go look at it to get a better understanding of that respiratory membrane. Now, what else do we have what else do we have going on here that's important? We have type 2 alveolar cells. This makes about 10% of them. They're small cuboidal cells that account for 10% of the cells there, and they produce a liquid called surfactant. You can see here, understand the purpose of surfactant. Let's just move this up, and we'll get to that. But let's also finish just up what happens at the alveolar wall. You see here, we have these macrophages. Alveolar macrophages. These are mobile macrophages that eat dead cells, dust, junk, pathogens, things that find your way into your lungs. You constantly need to have a pretty high amount of these cells to consistently eat all the junk in your lungs, because your lungs are probably how most people get infections, if you think about it. Because when we went back to the immune system, we have our primary defense, secondary, third. Now, you have to breathe in 20, 30 times a minute. Every single breath, you are taking something into your body. The body hates that. It needs it, but that also opens you up for infection. It's why so many diseases are found in the air, why you have to cough. So you need to have those macrophages all throughout your alveolar to make sure that you're cleaning up those bacteria and those pathogens before they actually can make it into your bloodstream. Now, let's talk about surfactant. Surfactant works similar to a soap or detergent. It reduces the it reduces the surface tension of water at the alveoli. Now, you literally have liquid in your lungs. Surfactant is liquid, and you would think, wouldn't that make it worse in terms of gas exchange? It's critical for gas exchange to actually work and to increase the amount of efficiency that your lungs can handle. Now, let's talk about soaps and detergent. When you clean your dishes or wash your clothes, it's a lot better to use soap. But if you haven't thought about why soap works, here's kind of the short version of it. You decrease the surface tension in water, and if there's a fat or something, you essentially make it easier to come off. There's a really nice figure 11.17, and we're going to pull it up here. If you don't have surfactant, the water molecules are going to start bonding together, because that's what water does. Surfactant reduces the tension and actually allows your alveolars to be full instead of starting to collapse, because the water that's in there is trying to stick together. Wait, you're saying that there's water in my lungs? Oh yeah, there's water in the air all around us. It's just in water vapor. However, if you didn't have the surfactant, your lungs wouldn't be efficient. All right, so now let's get into the real nitty-gritty of gas exchange. The first thing that we need to talk about is, I'm going to break this section up a little bit, is explaining Boyle's law. Now, Boyle's law is defined as this: relationship between pressure and volume and how they are inversely proportional. So, as the volume of a container increases, the pressure gas exerts on the container decreases. As volume of a container decreases, gas exerts on the container increases. Now, right now, I'm just saying words. They are important, but like all things, I think a picture is worth 1,000 words. So let's have a little picture here. You know how Microsoft Word is. You click one thing and picture goes anywhere. So this is explaining Boyle's law. If you can see here, we have a syringe with air in it. If you pull the syringe up, the volume increases, so the pressure is going to decrease. Next one, if volume is low, you depress the plunger and push it down, the pressure is going to increase. And if you think about this, you might be like, wait a minute, that's how my lungs work. Exactly. Boyle's law is able to perfectly describe how your lungs work and that relationship to gas, where gas and pressure gradients are going to determine everything about breathing in and breathing out. So, Boyle's law is all about the relationship between pressure and volume associated with gas, and that is how we are going to handle and explain gas exchange. Now, before we get into gas exchange, we have to get that air in and make it make sense. So, let's do pulmonary ventilation. Long and short, it's just respiration. So, we have inspiration. Breathing air in. Now, to breathe in, you also have to have breathing out. So inspiration is breathing in, expiration is breathing out. Now, this may sound really silly, but how do you breathe in? No, think about it for a second. Breathe in. We know that we are pulling our diaphragm down. The intercostal muscles are opening, so we are expanding our lungs. We're increasing our volume, which decreases our pressure. Now, there needs to be pressure definitions. So, interpulmonary pressure. Remember, look for those key words. Pulmonary. Pulmonary is referring to lungs. So the interpulmonary pressure has to be less than atmospheric pressure, the pressure outside. So at sea level, the pressure is going to be 760. This is going to, what happens to pressure as you go above sea level? This is why, I'll wait for a little bit. The pressure as you go higher and higher up in elevation is actually going to decrease, which is why it's harder to breathe as you get further and further up in elevation. So the interpulmonary pressure is less than this. This is what we need to breathe in. So we do this by increasing the volume in the lungs, by expanding those lungs. So when we breathe in, that decreases the pressure to under the atmospheric pressure, and when that happens, air is going to rush in. Now, it's the exact opposite for expiration. The diaphragm is going to relax, shrinking our lungs, decreasing that volume, and we are going to have interpulmonary pressure that is above the atmospheric pressure. So it sits at about 162, and they're going to equilibrate, that's not right, equilibrate, there we go, at 760 or wherever you are comparative to sea level. Because if you just sit here, and you're like more or less holding your breath, because if you don't, your body's going to breathe automatically, which thank God it does, otherwise life would be very taxing. But air isn't going to rush in and out. You have to actively change that pressure. You have to apply Boyle's law. This little plunger, that's your lungs and your diaphragm and your intercostal muscles working together. So let's see a nice little picture of it. Describe the process of pulmonary ventilation and the pressure changes associated with breathing in and out. You think of that balloon. Boom. Photo. You can see here that it has atmospheric pressure, interpulmonary pressure, and intrapleural pressure. Now, I didn't exactly talk about that because I'm more or less glossing over the pleural regions of the lungs. It's essentially a sac it's a liquid sac that your lung is essentially in. It helps and assists in the pressure gradient as well as keeping your lungs safe in terms of think about it kind of like a mini airbag for your lungs, so that if you get punched, your lungs aren't going to pop. The pleural helps distribute some of that pressure and that force. Anyway, we have in between breaths. The interpulmonary pressure is equals atmospheric pressure, 760, 760. Inspiration, we want to breathe in. The interpulmonary pressure and the intrapleural pressure decreases, so air rushes in. At that point, we have equilibrated again, so it's 760, so air isn't going anywhere until we breathe out. And doing that, we increase the pressure in our lungs. Air is going out. This is pulmonary ventilation, and it's incredibly important for gas exchange to get... Wait, which gas exchange? Pulmonary gas exchange. It's all about getting air into the lungs so that it can interface with the blood and swap that oxygen and carbon dioxide. So we can go back to the pulmonary gas exchange section, and we're going to fill this out a little bit more, because now we know this information. That movement of all gases is driven by those pressure gradients. Now, let's think about the air around us. Every time that we breathe, we are taking in oxygen. So we know air has to have oxygen in it. And again, it has to move with a pressure gradient. So PO2, when you see P when we're talking about the pulmonary system, it's referring to pressure or partial pressure in that system. So right now, this is air. So while PO2 in air, so the pressure of oxygen in the air is about 104, where blood has low PO2, about 40. This means, think about it, there's a pressure gradient here again. So you can go from the lungs to the blood because the pressure in the lungs, or in the air right now, is higher than in the blood. Now, how about carbon dioxide? That's not carbon dioxide. That is blood oxygen. 1 second. Found the right one. Pressure gradient favors carbon dioxide from the capillary blood into the alveolar air. It's not as steep, but it's aided by carbon dioxide's relatively high water solubility. It's easy to remember that carbon dioxide has high water solubility if you ever have had a soda before, or a sparkling water. The bubbles and the fizz and everything comes from carbon dioxide that is forced into that liquid. You can't really do that with oxygen. Now, there is a lovely photo that I'm going to include here. It's figure 2119. It's right here. So let's just fit this bad boy there, and let's look at it here. So this photo is essentially talking about the pulmonary gas exchange looking at pressure. So you can see here, oxygen is going in, carbon dioxide is going out, and it is because of this partial pressure gradient, which is Boyle's law. Now we're going to be taking a detour towards Dalton's law and Henry's law. So first one, Dalton's law. Each gas in a mixture exerts its own pressure, which then makes up the total pressure. Simple. I like to think about it like this. When you have a mixed drink or a cocktail at a bar, each individual component adds to that flavor. In air around us, that pressure, that flavor, is made up from all of that partial pressure. Those pressures are individual and they're additive. Each gas in a mixture exerts its own pressure that makes up the total pressure. Think about it like this. If oxygen has a pressure of 10, these numbers are not real, by the way, they're just made up. CO2 has a pressure of 10, and nitrogen has a pressure of 80. The total pressure is 100. Dalton's law was massive when it was discovered. Now it's kind of taken for granted, but each gas in the mixture has its own pressure and it's additive. Henry's law, on the other hand, is a little bit more important to what we're going to be talking about specifically for gas exchange when we're looking at gases in the blood. So, it's the degree to which gas dissolves in liquid is proportional both to partial pressure and solubility in liquid. Now, remember how I talked about earlier carbon dioxide? It has the lowest partial pressure of gases. In air, there's only about 1% of carbon dioxide compared to everything else in it. But it's dissolved in blood plasma because the solubility in water is 20 times greater than oxygen. Think about that soda. How it's so fizzy and so full of CO2, it's because it's super soluble in water. However, on the flip side, we have oxygen. It has a lower partial pressure in air than nitrogen. We're going to get to nitrogen in a second because air is 21% oxygen by volume. So when you're breathing in and all your life that you've said like, oh yeah, take those deep breaths, get that oxygen in. Most of the air is not oxygen. Most of the air is actually nitrogen. However, it's dissolved in blood plasma because it has more solubility in water than nitrogen. Lastly, nitrogen. It has incredibly high partial pressure in the air, just about 78%, but the amount of blood plasma is incredibly low because its solubility is incredibly low. This is going to make sense once you get into gas exchange, so if you're confused right now, don't worry, we're going to get to it right now. And if you're confused after that, then ask me a question, shoot me an email. So now we are at gas transport, movement of gases through the blood. We have two gases that we need to worry about, carbon dioxide and oxygen. We're going to start with oxygen first. Remember, as I said earlier, oxygen is better at dissolving in plasma than nitrogen, but nitrogen's god-awful at it. Oxygen's pretty crappy. Look at this. Only about 1.5% of inspired oxygen is dissolved in blood plasma because it has poor solubility. Instead, majority of the oxygen is going to be transported by hemoglobin. Now, we're going to do an entire section on hemoglobin when we talk about, right down all the way at the end, the oxygen carbon dioxide transport and the oxygen dissociation curve. Primarily, we're going to be looking at this. I'm kind of talking about this now, so let's just do this. Now, carbon dioxide, on the other hand. Let's get these numbers here. 7 to 10% of total CO2 is dissolved in blood plasma. But wait a minute, Austin, you were telling me about how good it was at being dissolved in water. So let's very quickly do oxygen, click, click, carbon dioxide, and let's get all of these goodies. So, 7 to 10% of carbon dioxide is dissolved in blood plasma. 20% of it is bound to hemoglobin. But 70% of the remaining CO2 is transported in a bicarbonate ion form. That is incredibly important for blood pH homeostasis. As we talked about earlier, where one of the secondary functions of gas exchange, or the secondary function of the respiratory system, is all about maintaining that acid-base balance. This is why. It's about carbon dioxide is incredibly important to maintaining this because we are dealing with that bicarbonate ion. Now, there's an entire process of carbon dioxide transport in terms of how it's able to stabilize and adjust depending on how it is in the blood and in the solution. I think because of all the material we need to learn, not going to talk about it, don't worry about it. However, the thing we will need to talk about now is the oxygen hemoglobin dissociation curve, which there is a photo of it right here, and if I can find it in the slides, we are looking at slide 45. Now, this is going to try to explain why oxygen binds to hemoglobin and how tightly hemoglobin is going to hold on to it. Because if you think about it, it would be really bad if oxygen would just, randomly be let go when it's traveling through the bloodstream. So this is talking about the percent saturation of hemoglobin on the y-axis, the partial pressure of O2 in blood, and it says here, as the hemoglobin is holding on to more and more of those oxygen molecules, the tighter it's going to bind. So, now I was going to explain it, but I took a second, and I actually, on slide 51, there is a video. So please go to slide 51 and watch this video. It's a lady who explains it incredibly, incredibly well, and I think that she actually does a great job of doing it, so I would recommend you to watch that. But remember, think about this. When it is super tight, it's going to hold on to it, and it doesn't want to let it go if it's not at a pressure gradient of an area. So we have to now talk about tissue gas exchange. So for tissue gas exchange, so we are now at the tissue gas exchange and really looking at that hemoglobin. We've talked a little bit about carbon dioxide, we've talked a little bit about oxygen, but now how do we get them to go across it with, remember Boyle's law, pressure gradient. So if you had to think, what do you think the pressure gradient is going to be at the cell? Cells use oxygen constantly for cellular respiration, so the pressure of oxygen in tissue is low, while the partial pressure in systemic capillaries is high. This steep pressure gradient favors the oxygen in hemoglobin to be given up and let go to go to that lower pressure gradient in the extracellular fluid. Now, think about carbon dioxide. We talked about this all the way back in the circulatory system, where we get carbon dioxide into the blood at the tissues because that is its waste product. So, tissues produce large quantities of PCO2, so partial pressure is high while it is relatively low in systemic capillaries. Boyle's law, Boyle's law, Boyle's law. So, let's put it all together. In a photo 2126, page 72. I'm going to drop it in here. Man, just doesn't want to. But let's go here so that we can explain it and see it. So, pulmonary ventilation. Remember, oxygen and carbon dioxide are moved in between the air and the lungs. Pulmonary respiration. We are bringing air in. We are going through the upper and lower respiratory tracts. We're going through the conducting and the respiratory sections, and we are moving oxygen in, carbon dioxide out. We're in the alveolus, that alveolar sac, and we have the capillary here. Oxygen has a higher pressure in here than in the blood, so oxygen is going to enter. Carbon dioxide, which was traveling through the blood, has a higher pressure in the capillary, so it is going to leave into the alveolus. Now, we're moving through the bloodstream, and we have to be very careful and very sure that the blood cell is not going to give up its oxygen until it reaches an area where those cells are demanding oxygen. So while oxygen and carbon dioxide are exchanged at the cell, this is going to be that tissue gas exchange. And again, remember, pressure, pressure, pressure. The pressure of oxygen here, low. Pressure of oxygen in here, high. Oxygen's going to go this way. Pressure of carbon dioxide in blood, it's high-ish, but remember, it's higher in the cells because they are constantly producing that as a waste product from cellular respiration. All right, last key concept for this section. What controls the rate and depth of ventilation? I said hint PCO2, the pressure of carbon dioxide. So the PCO2 is a major determinant for blood levels of carbonic acid and bicarbonate ions. Those are the byproducts of carbon dioxide and how it travels through the blood. It can either be in its bicarbonate or carbonic acid. One of these is basic, bicarb. One of these is acidic, acid. Those levels will fluctuate to keep that blood at a nice, healthy pH. Now, importantly, how is the PCO2 in blood? How does it determine it? Well, two factors. One, the rate and depth of ventilation. So how deep are you breathing, or how fast are you breathing? Are you hyperventilating or are you hypoventilating? The next one is the rate at which carbon dioxide is generated by cellular metabolic reactions. How fast are your cells burning through your energy and creating that carbon dioxide waste product? How fast and how efficiently are you bringing oxygen in and carbon dioxide out? So, for this reason, a change in normal pattern of ventilation can have a dramatic impact on the blood concentration of hydrogen ions. In the next section, we're going to talk about hypoxia, hyperventilation, hypoventilation, and what does that mean for it? Thank you much.